Hi, this is Mrs. LaBarbera. This is Physics Chapter 13, Modern Physics, Video 6. Today's topic is the nucleus. The objectives are know energy-mass relationship equation, understand the connection between energy and mass, and the fact that energy and mass can be converted into one another. Be able to determine the energy containing a given amount of mass. Be able to convert universal mass units into mega-electron volts, and be able to use or interpret a graph of energy versus mass. The nucleus is the core of an atom made up of one or more protons, except for one of the isotopes of hydrogen, and one or more neutrons. The positively charged protons in any nucleus containing more than one proton, and separated by a distance of about 10 to the negative 15 meters. In the nucleus, there are two major forces. One is a very large repulsive electric force between the protons. The other one is a very strong attractive nuclear force to keep the protons together. It is this strong nuclear force inside the nucleus that overcomes the repulsive electric force between protons and hold the nucleus together. Properties of strong nuclear force. It is charge independent. This means that in all pairs, neutron-neutron, protons and proton, or neutron and a proton, nuclear force are the same. At a distance of 10 to negative 15 meters, the nuclear force is attractive and very strong. It is about 100 times stronger than electromagnetic repulsion. The strongest force known to exist, the nuclear force, is also called strong force. The strong nuclear force is very short-ranged. So it ranges from about 0.7 times 10 to the negative 50 meters to 2.5 times 10 to the negative 50 meters. At a distance greater than a few nucleon diameters, the nuclear attraction practically disappears. So nuclear attractive force is weaker in larger atoms. So as the nucleus gets bigger, the attractive force between the nucleons gets smaller. So the nucleus becomes very unstable and start to break apart, causing radioactive decay. But what is inside here, if they are too close together, there is another force exists. That's a weak nuclear force in between 0 to. Obviously, the distance can't be 0 because the nucleons does have dimensions. Mass-energy relationship. So using many scientists' work before him, Einstein showed that mass and energy are different forms of the same thing and are equivalent. E equals mc squared. E is the energy in joules, m is mass in kilograms, and c is the speed of light in vacuum, which is 3 times 10 to the 8th meters per second. Let's do an example using that equation, E equals mc squared. Calculate the energy equivalent in joules of the mass of an electron. E equals mc squared. You can find the mass of an electron in the reference table, and that will give you 8.2 times 10 to the negative 14 joules. Nuclear mass and energy. According to Einstein's mass-energy equation, any change in energy results in equivalent change in mass. Mass energy is conserved at all levels, from cosmic to subatomic. In chemical reactions, if energy is released, then the total mass must be decreased. If energy is absorbed, then the total mass must be increased. Okay, let's take a look at atomic level. We don't use kilograms for mass. We use universal mass because the mass of nucleons are very, very tiny. Unit of energy, instead of using joules, we use mega electron volts. So the universal mass unit, or U, is defined as 1/12 of the mass of an atom of carbon-12, which is the carbon atom have 6 protons, 6 neutrons, and 6 electrons. In universal mass unit, the proton has 1.0073 units, and the neutron has 1.0087 units. I want you to pay attention here. The neutron actually is more massive than a proton. Even this information is not given to you in the reference table. The information given to you in the reference table to basically saying they are the same in kilograms, but in universal mass, we know neutron is a little bit more than proton. The mass of electron is 0.0005 universal mass unit. So in SI units, the mass of one universal mass unit, 1U, actually equals 1.66 times 10 to the negative 27 kilograms. We can use E equals mc squared to convert this U into joules. Then we can convert joules into electron volts and convert electron volts to mega electron volts. You will have this result, 1U equals 9.31 times 10 to the 2 mega electron volts. Nuclear energy is released from an atom through nuclear fusion or nuclear fission. So nuclear fission is a nuclear reaction in which nucleus of an atom splits into smaller parts, such as in the diagram here. This is a neutron is hitting uranium or plutonium nucleus. And this reaction will break up the uranium into smaller particles. And the whole process, the total mass will decrease. And this missing mass is converted into energy. In nuclear fission is the process when two or more, these are hydrogen isotopes, combine, they fuse together. During this process, the energy of the mass also decreased. It's called a mass defect. And this decreased mass, missing mass, is also converted into energy. So both processes are using to produce energy. And where is that energy come from? Two ways of mass energy conversions are when the mass is given in kilograms, you use E equals mc squared. When mass is given in U, you use 1U equals 9.31 times 10 to the 2 mega electron volts. Let's do a couple of examples. So according to the chart, tells you the rest mass of proton and neutron in universal mass. How do you convert the energy for the rest mass of a proton? Well, since mass is in U, we use 1U equals 9.31 times 10 to 2 mega electron volts. So basically you use the unit for proton times 9.31 times 10 to the 2. You have 9.4 times 10 to the 2 mega electron volts. Now energy required to separate 3 protons and 4 neutrons in nucleus of lithium atom is 39.3 mega electron volts. How do we convert this back into universal mass? So again, this is mega electron volts to U. We use 1U equals 9.31 times 10 to the 2 mega electron volts. So when you go backwards, you divide. So it's 39.3 divided by 9.31 times 10 to the 2. You have 4.22 times 10 to the negative 2U. Another example. This graph represents the relationship between mass and its energy equivalent. The slope of the graph represents, in order to find the slope of the graph, we have to find what's the relationship between energy and the mass. Energy equals mc squared. So the slope equals c squared. Another example, during the process of beta emission, a neutron in the nucleus of an atom is converted into proton, electron, antineutrino, and energy. Based on the conversion law, how does the mass of a neutron compare to the mass of a proton? So the mass and energy are conserved. So the mass of a neutron has to be equal to mass of proton plus mass of electron plus mass of antineutrino plus the mass equivalent of this energy. So how do you think they compare? Obviously, the mass of neutron has to be bigger than mass of proton. How does the charge compare? What is the charge has to be the electron antineutrino. So during this reaction, there are 3 things conserved. First is mass energy is conserved. Second, momentum is conserved. Third is the charge is conserved. The charge has to be conserved. Neutron has no charge. Proton has a positive 1. Electron has negative 1. We know energy has no charge. So what has to be the charge of electron antineutrino? So the electron antineutrino has to have 0 charge, no charge at all. That's it for today.